Hi again, this is Rory here to do the final sign-off for signal integrity on our design. Since we have done the automated checks with Hyperlink's DRC and the power integrity sign-off with DC drop and decoupling analysis, now we need to run a more advanced analysis with the DDRX wizard to verify our DDR4 memory. Wilfred did a less robust version of this without crosstalk earlier in the design cycle, and now it is time for me to check for any potential signal integrity issues we may have missed, now that the board is fully populated and routed. I will do this with a power-aware model. For this deeper dive simulation on the DDR protocol, the logical sequence is to first simulate the board uncoupled, which you can see the result of here. And then we will run the simulation again with coupling turned on, and then we will run a final simulation with our power-aware model. The idea is when I introduce additional effects, such as area fill coupling and trace coupling, my margin goes down. The more you idealize, the better the margins. So we are spending this time and effort to make a more realistic model of the board behavior before fabrication, and if we pass these checks, we can go into manufacturing with a greater peace of mind. If the board fails with ideal planes and no assumptions for PDN effects, noise, etc., then we know we have big problems. Since we have passed all the other simulations so far, now it's time to make sure it passes a more robust version of our board. Here I am enabling the trace coupling, and now you can see that it no longer has just the strip line, it has the coupled structure in the board viewer, and this at least has an influence on our impedance. So let's run the simulation again and compare. Notice that it takes a little longer to run now, and that's normal because all of these effects have an impact on our signal integrity, and as the simulation gets more complex, the execution takes a little more time. Looking at this most recent run, we see some minor changes here, and it's not that big, but it does have an influence on the impedance, and it is noticeable. For now, we do not see crosstalk, but this is one of the potential problems that we're investigating for. I will now turn on the power-aware model that I solved for earlier. We are modeling all of this behavior with an S parameter, and this includes the area fill coupling, the trace-to-trace coupling, via coupling, return path issues, cavity coupling, etc. With this S parameter, we introduce much more effects with the power-aware to the PDN than we did before, and therefore we can get a more accurate simulation of what the board will behave like in the real world once it's fabricated. This doesn't look too bad, so we can move on to the DDRX wizard for the advanced analysis and final report. Continuing on, I'll model one byte lane of the DDR4 to start, and then do this for all of the memory. Let's use the DDRX wizard to streamline the process. Remember, Wilfred, the PCB designer, ran the DDRX wizard earlier, but he was not modeling the effects that I'm modeling now with my power-aware model. I will include crosstalk check as well. I extracted the PDN, signals, and the vias with our hybrid solver and hyperlinks. Some effects can only be simulated with a model, such as the gate modulation effect that can be included in an IVUS model. The effect of modulation of the gate voltage is a result of power and ground bounce, and with the increase of the number of drivers, the SSN can deteriorate, affecting the voltage response at the output in a transistor level model. With these power-aware effects being modeled and included, we can get a clearer view of the impact on our circuit performance. The extraction of the S parameter for the power-aware model took a while to solve for, and as such, this simulation takes a bit more time to run because of the complexity of the model. The results and insight we get are well worth this time and effort, because if it passes, then we know our DDR signals will have a better chance of behaving as expected when fabricated. Looking at the report, we pass all of the data read worst cases, and we also have passed the data write worst cases. The report is nice in that we have clickable links. Here we can check out the eye diagram for the DDR4 signals. The eye diagram shows that we have enough margin for the real design. We passed the density and eye mask check. We can see a lot of margin for signal to noise ratio as well as for jitter. This means that we are well prepared for a real design. Remember, we use the advanced solver to create this power-aware model and have introduced additional PDN effects such as return current, cavity coupling, and via coupling. By passing with these real-life effects in our simulation, we are in really good shape here and can say that the board is verified for electrical sign-off and ready for manufacturing.